Let's introduce the idea of limits of a function. So a limit of a function is a value that the function is getting close to near a particular x value. So for example, if we look at this function right here, this function, x squared minus 4 over x minus 2, is not defined at x equals 2. We can tell that by the open circle here. So the graph has a hole at x equals 2. But notice on each side of x equals 2, right over here, if we look at the y values, we're getting closer to 4 in both directions. We're getting closer to the y value of 4. So we can see that by plugging in numbers that are getting closer and closer to the x value of 2, like 1.9, 1.99, 1.999, and then the other direction, 2.1, 2.01, 2.001. Now, notice 1.9 is right here, 1.99 here, 1.999 here, and the y values I'm getting back correspond to these values right here. On the other side, the 2.1 is right over here, and the 2.01 and 2.01, and these y values up here are the values that we're getting back that are close to that. In this case, we see both sets of y values are getting closer and closer to the y value of 4. So we write the limit, LIM, as x approaches 2 of this function is equal to 4. That's the y value we're getting close to as x approaches 2. So this notation, limit as x approaches a of f of x is equal to L, can be written if the following conditions are met. X gets closer and closer, but not equal to this value right here from the left and from the right, both sides. Then the corresponding y values that we get back get closer and closer to L. Another way to say this is the value of f of x can be made as close to L as desired by taking x arbitrarily close to a. I want to find the limit as x approaches 1 of x squared minus 3x plus 4. So I plug in numbers close to 1, like 0.9, 0.99, 0.999. Or on the other side, 1.1, 1.01, 1.001. If I plug in 0.9 to this expression, I would be going 0.9 squared. That would look like 0.9 squared minus 3 times 0.9 plus 4. If I plug that in my calculator, it's going to give me 2.11. Then 2.0101, 2.001, and so on. On both sides, we see we're getting closer and closer to the y value of 2. So we would write the limit as x approaches 1 of the function equals 2. And we can see graphically it takes on the value 2 near 1. Now, let's find this limit as we're approaching 3 for this function. Okay, so we're going to create a graph and a table of values. Now, 2x plus 1 is a line with a y-intercept at 1 and a slope of 2. That's this line. And 4x minus 5 has a y-intercept at negative 5 and a slope of 4. So that would be this line, but it only starts when x is bigger than 3. So we start drawing here and go up. Notice, as we get close to the graph this way, we're getting close to 7, and this way, we're getting close to 7. So we suspect the limit as x approaches 3 of f of x is equal to 7. We'll verify that with a table of values. Plug in 2.9, 2.99, 2.999. When I do, all those values are less than 3, so I plug it into this equation. 2 times that x value plus 1. These are the numbers I get. For 3.1, 3.01, 3.001, all of those values are bigger than 3. So we should be plugging it into this equation. 4 times that x value minus 5. If I do, these are the values that we get. In both cases, as we get close to 3, we see that we are getting close to a y value of 7. So we would write the limit as x approaches 3 of f of x is equal to 7. Let's do it here. Here we're approaching -2. So the values I choose are -2.1, -2.01, -2.001. And on the other side, -1.9, -1.99, -1.999. These are the values near -2. And I'm plugging this in as the x in this expression. So in my calculator, I'm going to put e to the -2.1 plus 2 plus -2.1 plus 1 over -2.1 plus 1. Now, there are two ways that I can plug that into my calculator. The first way would be to type it in. So I'd do parentheses for the numerator, second and my e to the x, and type in -2.1 plus 2, get out of the exponent, plus -2.1, so -2.1, plus 1, close parentheses for the numerator, divided by -2.1 plus 2. And then once I have that typed in, and I get my value back here, this is the y value, just hit second and enter to bring up the equation again, and now I can change all of those -2.1s to 2.01s. And you can use the insert key on your calculator, second insert, to insert a decimal. Another way that I could do it would be to go to the y equals and type in the equation. So parentheses again, second e to the x plus 2, so x plus 2, and then plus x plus 1 divided by x plus 2. And then I'm going to use the table of values to plug in values. So the first thing that I'm going to do is I'm going to hit second and format. And I'm going to change, second and table set right here, the window key. And I want to change the independent from auto to ask so that I can plug in values for the independent variable. Now go into your table. Let me see, it's blank here. But if I type in -2.1, it gives me the first value. And if then -2.01 and so on. And that'll allow me to fill out this table of values. We can see graphically we are getting close to that y value, but there's a hole there at -2. Use the graph to determine the limit as x approaches 1. As I approach 1, what y value am I getting close to? 2. Right? These values are getting close to 2. These values are getting close to 2. F of 1 is the closed dot. Its value is 3. Notice that my limit does not equal the function evaluated at that point. The limit is just about what we're doing on the left and on the right. It's not what's actually happening there. So for some functions, it's not true that the limit is equal to the function evaluated there. When this statement is true, that the two are equal, we call those functions continuous functions. If the limit does not exist, that means there's no single value that f of x approaches as x approaches a. For example, here, if I look at the left, 1.9, 1.99, 1.999, these are all less than 2. I'm plugging into this equation, and it seems to be approaching 3. From the right, 2.1, 2.01, 2.001, all these values are bigger than 2, so I should be plugging in here, and we see the y values are approaching 1. From this side, I'm approaching 3. From this side, I'm approaching 1, so the limit does not exist. And we can see that the two pieces don't meet up where the limit does not exist. Another way that the limit may not exist, if I look at the limit as we approach 0, plugging in negative values close to 0, it's getting large positive. Plugging in positive values close to 0, my y's are large positive values. But they're not approaching one single value. both are going up to infinity. So this limit does not exist. But we can say more than it simply does not exist. We can say that the way that it does not exist is that it's approaching positive infinity. Now, if instead on my graph, I look at like something like 1 over x, where one arm is going up and the other arm is going down near 0, then they're not both going the same way. So all I can say is this one does not exist. I can't write equals infinity there. Okay, so how does our limit fail to exist? Well, if they approach different numbers from the left and right, or if they're going up to positive or negative infinity, or if it oscillates between those.